Hello everyone and welcome to my presentation which titles towards data-driven optimization of mechanical performance of agricultural waste-based geopolymer concrete for sustainable construction. My name is Mohammed Ali Abdulrehman. I'm from Department of Materials Engineering, Mustansir University, Baghdad, Iraq. The construction industry is a major contributor to global CO2 emission. Ordinary Portland cement (OPC) alone accounts for approximately 7 to 8% of total world CO2 emissions, driving urgent research toward low-carbon alternatives. Geopolymer concrete. Alkaline activation of silica and alumina-rich precursors forms a 3D and ASH gel networks offering superior mechanical properties and durability while significantly reducing greenhouse gas emissions. Agricultural waste as a precursor, corn husk and packages are abundantly available and often underutilized. Controlled thermal treatment transforms them into reactive ashes rich in silica, ideal for geopolymer applications. The calcination challenges moderate temperature is around 600 centigrade favor for amorphous silica formation, while higher temperature above 700 centigrade induce crystallization, reducing uh, pozzolanic activity. Precise thermal control is essential. For raw material, corn husk, which abbreviation here as CH, and cigar sugarcane buckets were washed, oven dried at 105 centigrade, ground and calcined at 600 centigrade and 750 centigrade for 2 hours in a muffled furnace at 10 centigrade per minute. Fixed system. For the alkaline activator, we use 10 mol NaOH plus Na2SiO3 at ratio of 2.5, prepared for 24 hours prior to use for complete distillation and thermal stability. For mix design, 12 geopolymer concrete mixture from G1 to G12 were prepared with a constant liquid to binder ratio of 0.35. Replacement ratio of 50% to 75% to 100% were tested for each type plus hybrid combinations. For characterization, we use XRF for chemical composition, which measure oxides, and XRD for phases, and FTIR for functional groups for 400 for 1000 centimeter minus 1. And we use also laser diffraction for particle size, D50 and surface area. After that, we perform compression and flexural testing and tensile test after 28 days, and also water absorption and bulk density following the standard ASTM C642. 3 specimens per mixture results reported as mean plus minus standard deviation. For the chemical composition, XRF shows that silica was the dominant oxide across all ashes, and SCBA exhibits significantly higher silica content than CHA, directly enhancing geopolymerization. All samples exceeded the 70% combined Si2 plus Al2O3 plus FTO3 threshold per STM C618 for polyzonic material. For example, we can say from the oxide SiO2 at A600 around 62.37, and for Al2O3 around 5, and for CaO around 8, and for LiOL at 12.57. So SCBA recording higher silica percentage up to 78% versus 62 for the CHA. Higher silica directly promoted nice gel formation, and matrix densification. For LOL, the residual carbon impact axis 100 showed LOL around 12%, indicating unburned carbon that creates porous insulation, and increasing calcination at 750, reducing CHA to 10%, improving combustion efficiency. For the XRD, crystallization at 600 centigrade, both ashes shows a broad amorphous hump at 22 to 24 centigrade, 2 theta. Characteristics of reactive amorphous silica. SCBA at 600 centigrade exhibit the most pronounced amorphous character with minimum crystalline peaks. At 700 centigrade, sharp peaks for quartz at degree of to the degree of 26.6 and around 20 to 22 for the crystallite, more pronounced in CCBA, confirming parallel silica crystallization that reduces geopolymer activity. For FTIR, all samples shows dominant SI asymmetric stretching mode at 1095 to 1115. At 600 centigrade, the band was broad and less defined. At 750 centigrade, sharp combined with the peaks at 788 to 792, associated with the crystalline silica. CHA samples shows additional organic residual peaks at lower crystallization temperature consistent with higher LI value. FTIR findings strongly corresponding to XRD values. For comparison, at 600 centigrade, we have amorphous silica, higher reactivity, favorable for geopolymerization, minimum crystalline peaks. 750 centigrade shows the quartz and crystallite crystallization, reduced reactivity, sharper FTIR peaks, and lower geopolymerization formation. Particle fineness after ball mill grinding, CBA samples achieve finer particle sizes than CHA caused both temperature. B600 CBA 600 recording the finest particle. For D50 shows 14.2 micrometer and high surface area and 368 meter square per kilogram, tribute to its amorphous reliable silica structure offering less residual to comminution. For example, sample A16 shows D50 18 or a plane 315, and also for specific surface area 1.2 and assessment moderate. The highest value was at P600, 14.2 microsize, with the plane was around 368, specific surface area 1.47, and the value is high, optimum. 750 shows lower higher particle size, around 21.8, with lower specific surface area. 750 SCBA shows 16.4 with the lower specific area 1.3 and can be same good. The temperature effect on the grindability for both ash types. 750 samples were coarser than 600 counterparts. Crystalline particles are harder and more resistant to comminution, confirming that thermal history covers both erosibility and reactivity. Finer particles expose greater surface area to the alkaline activator, accelerating silica nominal dissolution and promoting denser and siliceous formation, directly reflecting the mechanical performance. For the mechanical performance, the conversion oxidant results after 28 days. The highest conversion oxidant was achieved by mix G2. You can 37.9 plus minus 0.8 megapascal, 75% SCBA calcined at 600 centigrade, comparable to the metallic based geopolymer concrete 35.8 megapascal. CBA mixture G1 to G2 consistently outperforms CHA mixture at G4 G6 across the replacement level. We can say the CBA 75% at 600 centigrade benchmark mixture was 37.9. For CHA 100% at 700 centigrade shows higher residual carbon, shows the lowest value for mechanical strength around 29.1 megapascal, and CHA improvement around 18%. And for the hybrid G10 shows the mechanical strength around 36.2. From that we can see the increasing calcination to 715 improve CHA, reduce carbon but reduce CSCBA strength due to the particle size partial silica crystallization. The optimal temperature is biomass dependent. For that, flexural tensile strength and physical properties. Flexural and splitting tensile strength followed by compressive strength trends, confirming that matrix integrity covers all mechanical properties. Mix G2 also led to flexural strength around 5.46 megapascal and splitting tensile strength 3.74. CBA mixture demonstrated superior tensile performance due to a more homogeneous cohesive matrix. CHA mixture showed lower values at 600 centigrade due to porosity from residual carbon, but improved at 750 centigrade. The density and water absorption, SCBA mixture exhibits significantly lower water absorption. G2 recorded the lowest at 5.21, indicating a denser, less permeable matrix. And for the CHA 100%, 600 centigrade recording 7.84, 50% higher than G2 attributed to the residual carbon porosity. CHA mixture shows significantly higher bulk density due to the denser and reacted particles, but SCBA mixture achieved better overall performance despite lower density, confirming that structural homogeneity and reactivity outweighs bulk density. You can say the value for the G2, G6 as CHA 100% 60 centigrade shows the higher value for water absorption flexural strength. As for the data-driven correlation and predictive analysis beyond trial and error, this study sustainability links precursor chemistry for the CiO2 content and the level to mechanical performance across the 12 mixture, providing quantitative framework for precursor selection. For the precursor selection, we prefer for the B600 SCBA from G1 to G3, when shows that silica 76%, level 5%, and mean strength around 36.77. But however, when we have higher silica, the value for the mean strength was reduced to 33. So the balance between for the low value of silica, we have the lowest mean strength around 30.4. So for the correlation, we can say the SiO2 versus strength. So when we say R squared 0.6 strong positive, and for the R around 0.38, for the Lul is around 0.83 is around strong negative. So higher reactive silica and lower residual carbon are jointly associated with improved mechanical performance. To conclusion, the best value for silica, we have to balance between the amount of silica and amount of fuel. We can say the highest value can be achieved when we add 75% SCBA plus 25% of the CHA 600 centigrade. with a mean strength of the 36.2 megapascal. Thank you very much.